downstream by constructing a dam. And in some places, these work with various degrees of success, but there's a lot of inherent problems with dams. One is that as soon as you build a dam, you're changing the river's gradient. You build the dam with the idea of filling a reservoir behind it and allowing that space to be filled with water. But as soon as you build a dam, it starts filling in with sediment because you've actually changed the gradient. The gradient behind the dam is zero, so as the stream approaches the reservoir, just like at a delta or the ocean, it deposits sediment on the bottom of the reservoir. So if your streams are carrying a lot of sediment, you can fill your reservoir with sediment really quickly. So all dams have a lifespan. Maybe they'll last a couple hundred years, maybe they'll last 1,000 years, but ultimately they won't last forever. The other problem with dams is that if your reservoir is, let's say, it's winter time and your reservoir is 80% full, and you get a big rain event, and so more water goes into it, and you of course release water from your dam, but usually dams can't release that much water. And if the rate of water coming into your reservoir exceeds the rate at which you're releasing water through the spillways of your dam, then the reservoir keeps rising. And there's been several instances in the past, including the one on the slide there, where either reservoirs got really close and they almost lost the dam that way, or as in the case of this one in Iowa, the water level in the reservoir actually got to the top of the dam and went over the top and then compromised and destroyed the dam. So lots of problems there. The other thing that can happen is if the dam's there, a lot of times that sense of security or that perceived safety encourages development downstream. The idea being, well, we have a dam there, we shouldn't have any more floods, so let's build this big community and that sort of thing. And then if you have a dam failure, you potentially compromise the safety of all those people downstream. Other things we build are levees. Levees are just big earthen berms along the banks of a stream. So the idea being that we build up the edge of the stream higher. But these have problems as well. How high is high enough? If you build, let's say you build a 3-foot levee above the stream, so the river can rise and fall. And as long as it stays below those 3-foot levees, everything's great. So what happens when you get a bigger flooding event? So it rises beyond those 3 feet. And now it not only causes flooding, but it breaches the levees. So levees can be very expensive. They have to be built along the length of the stream. So there's a lot of work involved in getting those things constructed. Again, not the perfect solution. Some communities at different points really channel this solution, something that humans have sometimes undertaken for well over 100 years. But the idea here is that we have a stream that's meandering, flowing this way and that way. And let's say we have 2 cities, City A and City B, and the different reasons for this. Maybe City A in ancient times, maybe they want to trade their particular distance to City B, and if you have to load that up on a barge and move it down 200 miles of the river, that takes a lot more time. If you can channelize your stream and just get it to go from point A to point B more or less in a straight line, maybe you can cut the distance in half. Sounds like a good idea, right? Efficiency, moving. Well, there's some consequences to this. Channelized streams are where they shorten the distance that the stream has traveled previously. Think about that. If the 2 locations, their elevations are fixed, right? They're not going to change elevation. But instead of this big meandering stream getting there, now you're going in a straight line, so you're steepening the gradient. So if the gradient of the stream becomes steeper due to channelization, what else would occur? So if it's steeper, then it's a lot steeper. So the water's moving faster. So if the water's moving faster, what it's doing is it's transporting more sediment, which will possibly erode the ground more substantially than it would otherwise. And so channelization also has its problems and impacts as well. It's detrimental to ecosystems and fish habitat and aquatic organisms. And what we've learned over time is, for the most part, this is not a good idea. A lot of communities have taken their previously channelized streams and now looking to restore them by putting in the meandering or the natural river setting and seeing good results from that. not just in terms of environmental results, but just water quality, all sorts of things. So our last thing here is looking at some different other solutions to flooding. Instead of focusing on something, what else can we do to deal with the flooding hazard? One thing we can do is just forecasting, so we can look at where is the topography of an area, rainfall patterns, and figure out where floods are likely to occur and with what kind of regularity. The key thing that we use for flood forecasting is this idea of recurrence intervals, which we talked about before with earthquakes. You've probably heard of a phrase like the 100-year flood. Now, what does that really mean? It doesn't mean that a flood occurs every 100 years on some sort of cyclical timeline. What it means is that on average, we get one flood of that size or magnitude or discharge level once every 100 years, on average. So you might have a 300-year period with no 100-year floods. On the other hand, you could have 4 100-year floods take place within 5 years, all based on average. Our flood records and our flood data only goes back maybe a couple hundred years, so it's incredibly data set that we have to work with here. But you can make some forecasts about how often floods occur using that kind of idea. One last thing on flood forecasting is this idea of probability. So let's say you lived in the 100-year floodplain. So you live in a location that, on average, has a flood once every 100 years. So what would be your probability? What would the chances be that your location is flooded in any given year? And the way to figure that out is to just do 1 over whatever your recurrence interval or your the floodplain you're in, whatever that number is. So 1 over 100 is 1%. So you have a 1% chance of getting a flood in any given year. And then what it comes down to is just, acceptable risk. Maybe you say to yourself, 1% chance of flood, that means there's a 99% chance of no flood. And so you opt to not purchase flood insurance. You don't really change your way of life at all. Full speed ahead, like not going to worry about this. Probably won't happen to me. And not the perfect solution. Some communities at different downstream. Other things we build are levees. Levees are just big earthen berms along the banks of a stream. So the idea being that we build up the edges of the stream higher, but these have problems as well. How high is high enough? Let's say we build a 3-foot levee above the stream, so the river can rise and fall, and as long as it stays below those 3-foot levees, everything's great. But what happens when you get a bigger flooding event? So it rises beyond those 3 feet, and now it not only causes flooding, but it breaches the levees. So levees can be very expensive. They have to be built along the length of the stream, so there's a lot of work involved in getting those things constructed. Again, not the perfect solution. Some communities at different points really channel this solution's, something that humans have